Swayam Prabha. Digital India. Educated India.
So, in the previous two lectures, we considered friction factors in fully developed laminar flow in regular section ducts as well as ducts of complex cross sections like any arbitrary cross section as long as they were singly connected. We now turn our attention to fully developed heat transfer. And like we did in the case of friction factor, we shall first of all look at very simple situations like the circular tube family, annulus and so on and so forth under a variety of boundary conditions. To do that, first of all we must define fully developed heat transfer. Consider this duct in which fluid at uniform temperature enters and there is a constant wall heat flux supplied at the wall. Then you can see that, the wall temperature will begin to rise and after some distance would rise at a linear rate. The bulk temperature, however, simply from first law of thermodynamics, that is m dot Cp into dt bulk by dx. Mind you, heat flux is constant and therefore, m dot Cp into dt bulk by dx into dt bulk will be simply equal to q wall into perimeter into dx, and therefore, dt bulk by dx will be simply q wall into perimeter divided by m dot Cp, and all these are constants. And therefore, you would see that the bulk temperature would rise linearly with x right from the start. We of course assume that the velocity profile is fully developed, may or may not be fully developed, and therefore, this shows the thermal development of the temperature profile. You can see it is started with a uniform temperature, but then as the heat flux comes in, it assumes a curved shape. Of course, the gradient at each section would be constant because q wall is constant. Ultimately, the profile would become like that. And since heat transfer coefficient is defined as q wall over T wall minus T bulk, this is constant. The difference between T wall minus T bulk is small to begin with, and therefore, heat transfer coefficient is high near x equal to 0, and it progressively drops as difference between T wall minus T bulk increases and ultimately becomes constant because T wall minus T bulk itself becomes constant. That is depicted on the left figure here. Now, let us consider another boundary condition which is frequently met, that of a constant wall temperature. This is like steam heating, in which the wall temperature is constant. The fluid enters at a value lower than the wall temperature, which is shown here, and the fluid bulk temperature would therefore start rising. You can see here, unlike the constant wall heat flux case, the bulk temperature does not rise linearly, but it rises non-linearly with x. To begin with, the gradient of temperature is very large, and therefore, at the wall, and therefore, h, which is minus k dt by dy at r or plus here, divided by T wall minus T bulk. So, although T wall minus T bulk is large, so is K dt dy at R is very, very large, and as a result again you get a variation of heat transfer coefficient H, which is very similar to that, in a constant heat flux case. So, that is what I have shown here. H goes on changing with x, but decreasing with x. The temperature profile of course becomes curved because of the thermal boundary layer development. Mind you, at each section the T wall will be same, only thing is the T center line will go on increasing, so that the T bulk goes on increasing, and this variation is non-linear as I indicated here. Of course, if the duct was very, very long, say going up to infinity, the bulk temperature itself would become equal to the wall temperature. In fact, the temperature at all radii will become equal to the wall temperature, but that would occur only at infinity, and it is not a case of importance in practical ducts which have limited length to diameter ratio. Fortunately, however, it so happens that as the temperature profile develops, the gradient at the wall goes on changing. As a result, the heat transfer rate goes on changing with x. A point is reached beyond which, although T bulk is changing and heat transfer, the gradient of the temperature is changing at the wall, a point is reached where K dt dr divided by T wall minus T bulk becomes constant, or H becomes constant. So, in heat transfer we say fully developed heat transfer is identified with constancy of H with axial distance. To show this, let us consider this. What does this imply for the temperature? So, we define, for example, phi as a function of x and r in case of a circular tube as T wall x minus T x r divided by T wall x divided by T bulk x. Now, when you T wall and T bulk can only be functions of x, where T bulk is of course rho Cp u T dA and rho Cp u dA, where dA is the A is the area of cross section. In fully developed heat transfer, we say that d phi by dx will be 0. The dimensionless temperature profile will go to 0, or essentially dimensionless temperature profile will become constant with x. And since phi is constant with x, we would expect that d phi by dr at the wall will also be constant with x, which of course means that it is equal to minus dt by dr r equal to r divided by T wall minus T bulk x equal to Q wall over T wall x minus T bulk x. This definition is used for constant heat flux case. This definition would indicate definition of H in case of constant wall temperature, and you will see that that H becomes constant. So, fully developed heat transfer constancy of H implies that d phi by dx must be equal to 0. It is the dimensionless temperature which must be 0. Remember, we defined fully developed flow where du by dx itself was equal to 0. In heat transfer, we say fully developed dimensionless temperature gradient with x is 0 is the condition for fully developed heat transfer, and it implies H equal to constant. Although T wall and T bulk and indeed temperatures at every radius may vary with x and r, but as long as T wall, T bulk and the heat flux, that ratio remains constant or H is constant, we say the fully developed heat transfer has been reached. So, let us take the first case, the simplest case which you have studied in your undergraduate course, and that of a circular tube with constant heat flux at the wall. So, in that case, the governing equation, as you will recall, is simply 1 over r d by dr r dt by dr equal to u divided by alpha. Alpha is a thermal diffusivity k by rho Cp into dt dx, but since q wall is constant, dt dx would be replaced by dt bulk dx, and it will actually also mean dt wall by dx from our definition. You can see if dt bulk by, if I were to say d phi by dx equal to 0 and dt x equal to dt bulk x, then dt wall by dx will also be 0. To make it explicit, let us say d phi by dx equal to 0 would imply that where phi is equal to T wall minus T divided by T wall minus T bulk, and this would imply 1 over T wall minus T bulk into dt wall minus T by dx minus 1 over T wall minus T over T wall minus T bulk squared dt by dx T wall minus T bulk equal to 0, which essentially gives me dTw minus T by dx equal to T wall minus T over T wall minus T bulk into dt wall minus T bulk by dx, which implies that all dTw by dx is equal to dt by dx and is also equal to dt bulk by dx. The implication is that all, once the fully developed flow is reached, temperatures at all radii increase with constant with x equal to, and at all radii dtx is equal to simply dt by dx. So, you will see that dt bulk by dx, of course, is simply, this is m dot into Cp and this is q wall into perimeter, which of course is a constant, and therefore, the equation would simply become 1 over r d by dr r dt by dr, and fully developed flow in a circular tube is given as 2 u bar 1 minus r square by r square, and therefore, this would be that. So, if I integrate this equation twice with boundary conditions T equal to T wall at r equal to r and dt by dr equal to 0 at the axis of symmetry, then I can determine two constants of integration, and the result is shown on the next slide here. T is equal to T wall minus 3 by 4 q wall over k r plus q wall over k r into r square minus r 4 r. Now, of course, I evaluate T bulk, which is you will recall, and we assume constant properties. So, rho Cp just cancels, and if I were to substitute this for temperature and the velocity profile from the previous slide, then I would get Tw minus 11 by 24 q wall over k r. Now, remember, in all these cases integrations are very important, and you have to take a lot of care to make sure that you make no errors in evaluating the temperature, in evaluating the integrals. So, you can now see that Nusselt number, which is defined as h d by k, it will be equal to 2 r by k q wall over T wall minus T bulk, and T wall minus T bulk is 11 by 24 q wall r by a. So, that gives us 48 by 11 equal to very well known result 4.3636, which you derived in your undergraduate course. A similar analysis for flow between parallel plates, which are separated by a distance 2b. Say, if I have two parallel plates and the distance between the plates is 2b, and if I measure y from the axis symmetry, then u fully developed divided by u bar in this particular case is 3 by 2 1 minus y by y square by b square, as you recall. And if I carry out the similar analysis for constant heat flux at both the walls, then the answer I would get is based on hydraulic diameter. Remember, the hydraulic diameter for plate distance of 2b, dH is 2 times the plate distance, and that is equal to 4b. So, H 4b by K will give you 8.235. Very simple cases that can be done by pencil and paper integration, no difficulty at all. You do not need numerical integration or anything like that. Let us now turn our attention to a little bit more complicated thing. Again, I am going to consider now a flow in an annulus. Flow inside an annulus. You can get variety of it. May be heated from inside or it may be heated from outside, Q wall O or Q wall I. So, we are going to consider this particular case, in fact, both the cases in turn. So, let us look at, you will recall from our earlier analysis that fully developed velocity profile is given as 2 by m 1 minus r by r o square plus b ln r by r o, which has a logarithmic term in it, and b itself is this, m is this, and r star is r I by r o, the radius ratio of the annulus. The equation proper, of course, remains the same. It does not change at all. Only thing is dt dx here will be dt bulk by dx, and that would be equal to 2 pi r o q wall o plus r I q wall I divided by rho c p u bar pi r o squared minus r I squared. We can have two types of boundary conditions. In the first case, outside wall is heated. So, q wall O is given equal to k dt by dr at r o, and the inner at the inner radius r I we have T w I. On the other hand, we can also have a case in which the outer inner heat flux is given and the outer wall temperature is T w O. Annulus solution. So, if I integrate this particular equation with substituting for dt by dx dt bulk by dx and u f d equal to this, and integrate this equation twice, which is, mind you, quite a elaborate integration because logarithms are involved, I would get temperature itself as that, where A itself, A the multiplier of this square bracket is this, and Q star is inner wall heat transfer divided by outer wall heat flux. I will consider two cases, as I said. In the case 1 where outer wall is heated, C1 turns out to be this and C2 turns out to be this. In the other case where inner wall is heated, it will turn out to be this and C2 is equal to that. So, mind these things require very careful algebra in order to avoid any errors. I can express the solution that of the previous slide in a more compact form as T minus T w O Q wall O R O by K, which has dimensions of temperature. Q wall R O by K has dimension equal to 1 over m into 1 plus Q star R star plus mind you Q star is Q wall I minus Q wall O, 1 minus R star is R I by R O whole squared, multiplied by a function f 1 minus function f 2, and I have given here the values of f 1 and f 2. We now define, let us say in case 1 where Q wall O is heated, I will define NuO equal to at the outer wall HO dH by K, where the heat transfer is specified, and that would be equal to Q wall RO by K T wall minus T bulk into 2 into 1 minus R square. Remember, this is nothing but for the annulus dH is equal to 2 times RO minus RI, 2 times RO minus RI, and that is what is reflected here. So, if I take RI common, you will get that. So, with this temperature now, you must evaluate the bulk temperature. Mind you, the bulk temperature evaluation becomes extremely difficult because there are logarithmic terms involved, and numerical integration is the best way out. It does not require too much effort. For case 2, where inner wall is heated, that is Q wall I is given, the solution can be expressed compactly in this fashion: R star square by m into 1 over Q star plus R star or that multiplied by a function f 3 plus all this, and f 3 itself is given by a long expression like that. Mind you, these expressions take quite a bit of algebra to arrive at. And again, in this particular case, I will define NUI equal to HI dH by K equal to Q wall I RO by K divided by T wall I minus T bulk into 2 into 1 minus R. Again, using this temperature profile, I must evaluate T bulk, which is required here by numerical integration. It is very fortuitous that the NUI NUO for a variety of radius ratios can actually be expressed in the form I have indicated. NUI would be equal to NUII into 1 minus theta I by Q star, and NUO can be expressed as equal to NUOO into 1 minus theta naught minus Q star, where NUOO and theta O, NUII and theta I are simply functions of the radius ratio. Now, remember, Q star was actually equal to QWI divided by QWO is equal to theta I. If suppose that was equal to theta I, then this gives a odd result that NUI would be equal to infinity. But that should not worry us, because all it implies is that it does not imply infinite heat transfer, but simply that the inner wall temperature turns out to be equal to the bulk temperature, and therefore, NUI goes to infinity. Similarly, if Q star is less than theta I, say Q star is less than theta I, then NUI will turn negative, which implies negative HI. But again, as we said repeatedly, that this is not a particularly unacceptable situation. All it implies is that since NUI is negative, T wall must be greater than T bulk. T wall I must be greater than T bulk. I beg your pardon, T wall I must be less than T bulk, and as a result, the NUI has turned out to be negative. So, similar arguments would apply, of course, to NUO. So, values of NUII, NUOO, theta I and theta O are given on the next slide. But mind you, to write the previous solutions in this manner, you again have to do little bit of algebraic manipulation to show that this theta I and NUII are functions of radius, and only Q wall minus Q wall I over Q wall O separates out as a function. So, here are the solutions that I present from R star equals 0, which is the circular tube, and you can see NUII has no meaning, but NUOO is 4.364 and its influence coefficient is 0, and therefore, NUO itself, as you can see here, influence coefficient is 0 and NUO would be equal to NUOO, and therefore, that would be equal to 4.364. As I go on increasing the inner radius, then you can see that the coefficients and the NUOO values go on changing. When R star becomes 1, you essentially have flow between parallel plates. In this case, both NUII and NUOO and theta I and theta O are exactly identical, and therefore, as they should be, and our table confirms that they turn out to be the same. So, usually Nusselt numbers are not readily available for annulus, but with this method you can see now you can evaluate them for any any situation for any Q wall I, any Q wall O that may be prescribed, and you can readily recover the solutions for entire family of annulus solutions. I will deliberately consider now a problem in which I am considering flow between parallel plates, that is the last entry in that table. Let us say this is Q 2 and this is Q 1. The velocity is fully developed. So, if you read the problem, it is like this: the flow between parallel plates which are 5 centimeters apart. So, therefore, dH will be 10 centimeters, and I have said Q 1 is equal to 1 kilowatt per meter square, and this is 5 kilowatts per meter square. Of course, since the flow is fully developed, the bulk temperature is rising with x, and I am simply considering the k x actual position where T bulk is 30. T bulk is 30 degrees centigrade, and the conductivity of the fluid is 0.2 watts per meter Kelvin. The question is, what will be TW1 and what will be TW2? That is the question that I asked. So, for example, the solution would run something like this: NU1 will be H1 dH by K equal to NU11 over 1 minus theta 1 Q star. And if you see, the influence coefficient for parallel plates is 0.346, NUII is 5.385, and therefore, the NU1 will become 5.385 1 minus 0.346 divided by Q star, which is 0.2, and therefore, the Nusselt number turns out to be negative 7.377 minus 7.37, and therefore, the heat transfer coefficient will also turn out to be negative minus 14.753, and since Q wall is 1 kilowatt, H1 is minus 14.753 and T bulk is 30, I can evaluate TW1 as minus 37.8. So, TW1 evaluates to minus 37.78 degrees centigrade. What about the outer wall? You can do the same thing, NU2 equal to H2 dH by K equal to NU22 minus 1 minus theta 2 into Q star, and again you will see NU2 will turn out to be 5.785, H2 in this case will be 11.57, and TW2 turns out to be 462.112. You can see what a great temperature difference there is. So, basically you have a situation where very high temperature on this side and a very low temperature on this side. So, minus 38 here, 462 here, and the average temperature is 30 degrees centigrade. It is for this reason that we are interested usually in finding out the solutions, because the wall, no wall should become too hot or too cold, because it might affect other processes on outside or inside of the annulus. So, in as much as the bulk temperature is only 30 degrees centigrade, the wall temperatures can be enormously different for just very small heat fluxes of 1 kilowatt to 5 kilowatt meter square. So, it is for this reason that we take particular care in evaluating our Nusselt numbers accurately in annulus flows. I turn my attention to circular tube heat transfer, in which TW is constant, actually constant. and the flow is fully developed. So, you can say that in this particular case nu sub t means T wall is constant, it will be h 2 r divided by k, and that would be equal to dt dr at r into 2 r divided by T wall minus T bulk, and that should be a constant, because h itself we say the fact that it is fully developed means h is constant, and therefore, Nusselt number is a constant. Then if you go back to slide 2 and recall that this is the condition for fully developed heat transfer for h equal to constant, then you will see that dt by dx would be simply phi times dt bulk by dx, and dt bulk by dx would be from heat balance 2 alpha divided by u bar r equal to q dt by dr. Remember, k dt dr at r equal to r is simply the heat flux that is coming in, and therefore, dt bulk by dx would be related to dt by dr at the wall. So, if this was the original equation, and if I now substitute for dt dx in terms of phi, then this will transform, the equation would transform to this form: d 1 over r d by dr r star d phi by dr star equal to minus 2 nu t phi into 1 minus r star square. This is nothing but a second order ordinary differential equation with a boundary condition that phi r star at 1 which is the wall, it is equal to 0, phi is 0, and d phi by dr star at the axis of symmetry is 0, because it is a symmetry line, and r star is equal to r divided by r. So, this kind of a second order ordinary differential equation is really solved by shooting method as I show you here. So, what one does is that, let us say this is r star and we want d phi by dr star equal to 0. The actual value of phi would not matter, all that we want is d phi by dr star equal to 0. It is a dimensionless quantity, and we say d phi by dr star is equal to 0. So, we assume a value of Nusselt number and solve the ordinary differential equation on a computer perhaps, and you will come up with a value of phi at r star equal to 1, which is the wall, where we want phi star to be 0. If our nu guess was incorrect, then the chances are that you will come up with this. So, this is nu guess 1. Obviously, it is not equal to 0 as I wanted. So, I take another guess, and you will see I may come up with that nu g 2, and the error now is on the positive side. The error here was on the negative side, and therefore, I can use a bisection method to refine my error and generate a solution. Ultimately, I will come up with a value of n, which gives me phi at r star equal to 1 equal to 0, which is what I want. So, this is the nu correct. This would be the correct value of nu, and if you do that in this equation, you have to go on assuming a value of nu t and solve the equation, and you will see nu t turns out to be 3.656, or sometimes taken as simply 3.66. It is also possible to solve this equation analytically in a series form, and the solution has been given here, and again the value of nu t works out to be 3.656. If I were to do this same problem for flow between parallel plates with T wall equal to constant and T wall equal to constant on both sides, then the Nusselt number that I would develop is 7.545, but that I leave you as an exercise to be done. We now turn our attention to one more case, and that is the case of highly viscous fluids flowing in a tube, highly viscous. So, its Prandtl number is much greater than 1, Prandtl number is much greater than 1, in which case there is a constant wall heat flux applied. In that case, you will recall from our energy equation that because viscosity is very high, viscous dissipation term mu du by dr whole square becomes as important as the conduction term, and therefore, it must be retained in the energy equation. UFD of course, is 2 u bar 1 minus r square by r square, and dt by dx equal to dt bulk by dx is equal to constant. DUFD by dr square from this thing will evaluate to 16 u bar square r square by r 4, and therefore, substituting these things in here, I get 2 u bar by alpha 1 minus r square by r square dt bulk by dx equal to 1 over r d by dr r dt by dr plus 16 times mu by k u bar square r square divided by r 4. This is equation A 2 and the original equation is A 1, and the boundary conditions are again at the axis of symmetry this would be 0, and at the wall it is equal to q wall equal to k dt dr. The main thing is I said dt bulk by dx will be constant, but what will be its value? That is what we need to evaluate. So, to do that on the next slide, what I will do is I will simply integrate this equation. So, you can see the left hand side, if I integrate over area of UFD, and because DUFD by dx is equal to 0 because it is fully developed, UFD dt by dx will actually become d by dx of UFD into temperature, and I integrate this d by dx of 0 to r UFD T dy. Then you can see this gives me dt bulk by, this will give me dt bulk by dx, because this when this is divided by integral 0 to r UFD dy, I mean dr, r dr rather, this is the definition of T bulk, and this is a constant u bar r dr is nothing but a mass flow rate through the channel or through the circular tube. So, you will see that to determine dt bulk by dx, I would simply integrate this equation from 0 to r on both sides of this equation. The left hand side will give me dt bulk by dx. This I will evaluate because I will get r dt dy dr at the wall and r dt by dr at the axis, which is 0, and I will substitute q wall, which is known for the upper boundary condition, and likewise you integrate this from 0 to r. The result is dt bulk by dx would turn out to be 2 q wall alpha k u bar by r, which is the case when there is no viscous heating is included. But now you see that the bulk temperature rise is also influenced by the amount of viscous heating that has taken place, and that is the equation A 3. So, if I substitute dt bulk by dx in equation A 2, which is this equation. So, if I substitute for dt bulk by dx, I will have an equation which looks like this. I must integrate this equation twice and determine two constants of integration to determine the temperature profile. The temperature profile looks something like this. Remember again, if mu was 0, that is if viscous dissipation was neglected, then that term would be 0, and here that term will, and we will recover our original case of solution without viscous heating. And the T bulk then evaluates this temperature must be integrated with U f d, and T wall minus T bulk would evaluate to 11 by 48 q wall d by k plus mu u bar square by k. And therefore, now it is very easy to define if I divide both sides by q wall d by k, then the Nusselt number would be obtained as here 11 by 48 plus mu u bar square divided by q wall d raised to minus 1. And this quantity is called the Brinkmann number after the scientists who first solved this kind of a problem. And this can be written as 192 divided by 44 by 192 multiplied by Brinkmann number. Of course, if Brinkmann number is 0, then you would readily recall 192 by 44 equal to 4.364. So, the effect of Brinkmann number for high Prandtl number fully developed heat transfer becomes very higher the Brinkmann number, depressed would be the heat transfer coefficient. I now consider the case of liquid metals when Prandtl number is very small. As you will recall, for liquid metal the Prandtl number is less than 0.01 usually. Prandtl number is less than 0.01, and therefore, the actual conduction term which we have been neglecting so far becomes important, particularly when the wall temperature is constant. Wall temperature is constant and you have liquid metal heat transfer. Then the governing equation would look as I have shown here. There will be the radial conduction term and the actual conduction term equal to UFD by alpha dt by dx. Now, of course, this is now a two-dimensional equation. It involves dependent variables r and x. It can be solved analytically or nowadays much more simply by finite difference method, and I give below the finite difference method solutions for different values of Peclet number. Now, I want you to appreciate how Peclet number comes about. So, the governing equation is 1 over r d by dr r dt by dr plus d2t by dx square equal to UFD divided by alpha dt by dx. Now, if I define x star is equal to x by r and r star is equal to r by r, then you will notice that this will become simply 1 over r star d by dr star into r star dt by dr star plus d2t by dx square r star square equal to UFD by alpha dt by dx star into r. And you will see that this becomes and there would be 1 over r star here also. So, if I multiply through by r star r square, then you will see this becomes d by dr star into r star over dt by dr star plus d2t by dx star whole square is equal to UFD r divided by alpha dt by dx star. And what is that? UFD into r divided by nu into nu divided by alpha. If I do that, then you will see that this is Reynolds number divided by 2 and this is Prandtl number nu divided by r. The product of Reynolds and Prandtl is called the Peclet number. So, this is essentially Peclet number divided by 2 dt by dx star, and therefore, the equation can be written as Peclet number into 1 over r star d by dr star r star dt by dr star and so on and so forth. So, the Peclet number essentially determines the behavior of the solution. I have obtained this, remember because Prandtl number is so low, the product of Reynolds and Prandtl can be very low in laminar flow. So, I have taken values of 0.1, 0.51, 1.5, 2, 3, 5, 7.5 and 10, and obtain solutions by finite difference method. And here are the solutions. For very low Peclet number, the Nusselt number is 4.057, but as I increase the Peclet number, which means allowing for more and more actual conduction, then you will see that this becomes even more, the Nusselt number goes on reducing, and when Peclet number is about 10 and the wall temperature is constant, mind you. So, at large Peclet numbers, the actual conduction effect goes on almost becoming negligible, and you arrive at 3.85. In effect, as Peclet number tends to 0, you get only constant heat flux solution. So, Nu equal to 0.364, and as Peclet number tends to infinity, you get the constant wall temperature solution 3.667. There is yet another case of considerable interest which you might like to know. And this is the case of a tube which may be receiving, let us say, radiant heating. Then clearly around the circumference it will have a variable heat flux Q wall theta, although actually it will be constant. At each cross section, Q bar will be simply 0 to 2 pi 1 over 2 pi Q wall d theta would be a constant with x. So, this is a case which will occur for radiant heating. Sometimes it will also occur for a tube of uneven thickness, let us say, and it is being electrically heated. So, there is internal heat generation within the tube, and therefore, it will receive circumferentially varying heat transfer. So, in that case, the equation would become, again, because of the constant heat flux condition, dt bulk by dx would be constant given by that, and but now you must allow for conduction both radially as well as in the circumferential direction. Again, this 2D equation can be solved both analytically or by a finite difference method, and for Q wall theta as this a simple circumferential variation of heat flux, the solution turns out to be this 1 plus b cos theta 11 by 48.5 b cos theta, where b is simply a parameter. So, you can see in this case Nu theta along the periphery of the duct can assume both positive as well as negative values, but that should not disturb you, because that is expected. All it tells you is whether the T wall bulk is greater than T bulk or less than T bulk. But if b is equal to 0, which implies Q wall theta is uniform along the day, then you readily recover 4.364, and that is what we had. So, this particular type of problems are very, very important, because hot spots have to be avoided on walls when you have uneven heating on all the sides. In the next lecture, we shall consider heat transfer in non-circular and arbitrary section ducts.